the basic introductions of colloid. So before moving to the main topic, let us just wonder about this beautiful picture. This is a picture of milk, colloidal milk. So you can see the red spots. These are nothing but the milk particle, that is the fat oil particles. It is an oil in water emulsion. And we have the black background, that is the liquid part, and here it is the V. So these colloids are really fascinating molecules, and they are the molecules that control our life, that controls all our activities, because most of these particles are also biologically active molecules. And let us move to another slide. This is another beauty of colloids. So you see, this is the popular what we call the Tyndall effect, simply by passing light through milk water suspension. This is a colloidal solution, of course, not a suspension. And if you just pass light through it, you get through one with a transparent glass, another with a milk, you can see the beautiful sunset. Okay, that is the Tyndall effect, the scattering of light by the colloidal particles present in the milk colloid. And finally, with another slide, if I'll try to move to my topic. So when we really take the image of photograph of the colloid, they look like this. This is the scanning electron microscope image of titanium oxide colloid at two different particle size, 1 micrometer and 200 nanometer. So you can see how beautiful they are, and they are not only beautiful, they are one of the most fascinating molecules that controls our activities, that controls our biological as well as our daily activities. So it is really interesting molecules. So today we'll only briefly go to the topics that I have discussed regarding colloids. So let's start my talk. So let's begin the talk with the origin of the word colloid. So we all know this term colloid comes from the Greek word kolla, which actually means glue, and eidos meaning like, that is glue-like particles. And this was first used, and even it was first discovered, and the word was first used for the first time by none other than Thomas Graham, who is also called the father of colloid chemistry. So way back in 1861, he coined this term, and what was his purpose? He wanted to distinguish glue-like material that generally do not pass through Tocqueville filter paper, while the majority of the substance, they generally pass through them with ease. So he also coined another term, that is crystalloid, for those substances which readily pass to Parkman filter paper. So those which cannot, we call colloids after glue-like, and those who cannot pass through the Parkman member, crystalloid. Because why? They can be crystallized from the solution. So that is about the terminology of the word colloid. So the father of chemistry is definitely Thomas Graham. Okay, before going to the main aspects, let's have a brief refreshment of the word colloid that we have been learning since our school days. And in high secondary, we have a detailed discussion about colloids. So when we say colloids, we generally means particles, and they are definitely particles of nano size, and we keep the range between 1 and 1000 nanometer, and they are they are generally called dispersion because the particles, they don't settle down but remain dispersed. And one other interesting feature of the colloid, that these particles generally carry electric charge. And another thing, that all the colloidal particles carry the same electrical charge, but still the colloidal solution is electrically neutral. Why? Because the dispersed phase has one charge, but the medium takes the opposite charge. So another thing is, because of the presence of electrical charge, there is electrostatic repulsion. These repulsive forces force them to remain dispersed, and they cannot agglomerate or aggregate together as precipitate. And that is, they maintain the stability of the colloid. So this is about the very simply what are colloids. Now the most interesting feature of colloid. So generally when we talk about stability and when we talk about thermodynamic stability, we have to go to the parameters, thermodynamic parameters, basically free energy. So colloidal dispersion is inherently thermodynamically unstable system. Why? Because these systems in the formation, they try to minimize surface energy. When they try to do so, okay, the interfacial free energy increases. So they have very high interfacial free energy in the dispersed state. Okay, so they try to, so in order to minimize this interfacial free energy, in order to go towards a system of lower free energy, it tends to agglomerate. So from thermodynamic point of view, they are unstable. So that is, it refers to the situation in which the coagulated phase has lower free energy. Dispersed phase has higher free energy, so they don't want to stay in the dispersed phase. They want to move to the coagulated phase, to the precipitated phase, which has lower free energy. So when we say about stability, so in terms of thermodynamic, we say that colloidal dispersion is thermodynamically unstable. But interestingly, why they exist? If they are inherently unstable, thermodynamically unstable, they have kinetic stability. How we can say about that? How can we, since they exist and they exist for a long period of time, that is, their lifetime is quite high, this indicate that they do have kinetic stability. Now what gives them this stability, or what is the source of this kinetic stability? Definitely the thermal energy. Thermal energy is generally, if you go to the Boltzmann equation and other distribution laws, you will find this thermal energy is nothing but product of the Boltzmann constant Kb into T. So this is this energy that they possesses, and that they, through which they acquire kinetic energy. So they are constantly moving within kinetic energy because of thermal energy, okay, the kBt. But since they have charges, okay, and the charges on the particle surface, they provides an energy barrier, an activation energy is provided, and this has to be overcome if they want to go to the aggregated state. If they want to coagulate, they have to overcome this energy barrier. And interestingly, this energy barrier is much larger than the thermal energy of the molecule kBt. So in spite of having a lot of thermal energy, which is numerically equal to Kb into T, they do not aggregate, they remain in a dispersed state because of this energy barrier, which is created by the surface charge on the particles, and which is higher than the thermal energy. So the kinetic stability is due to the existence of the energy barrier, and the thermodynamic instability is due to the higher interfacial free energy. So thermodynamically they are unstable, but kinetically they are stable. So this is when we broadly speak about colloid. But mind it, there is one inherent distinction there is one point to be noted in this generalization. So generally we say that colloids are thermodynamically unstable but kinetically stable, but we have to keep in mind that this is not a complete generalization. Why? So that is why we often go to the basic classification of colloids based on stability. So though we say that colloids are thermodynamically unstable, kinetically stable, but there is also a thermodynamic stable state in the colloid, and that is nothing but the lyophilic colloids. The colloids in which the dispersed phase and dispersion medium has strong affinity. This type of colloidal system do have thermodynamic stability. That means in their dispersed states, they have lower free energy than that in the coagulated state. So they prefer to stay in the dispersed phase. And we know the lyophilic systems like proteins, which are biologically active molecule, they always prefer to stay in the colloidal state. Why? Because they are thermodynamically stable. But what about the other systems, that is the lyophobic system? They are kinetically stable. So that means in terms of stability, we can classify colloids as thermodynamically stable lyophilic colloids and kinetically stable lyophobic colloid. But often we generalize it that colloids are thermodynamically unstable but kinetically stable. That means we generally refers to the lyophobic colloids. So when we use that particular statement, our complete visualization will be not on lyophilic but on lyophobic colloids. So in case of lyophilic colloids, what actually happens? So the dispersed phase and the medium, that is solvent-solid interaction, is quite high, and that is their basic criteria. Lyophilic, the medium and the phase have strong affinity. So as a result, what happened? The dispersed phase is highly solvated by the dispersion medium. The molecules of the dispersion medium surrounds them, entrap them, case these dispersed particles. And as a result, we have a single dispersion of macromolecules. So if you see examples of lyophilic, basically they are polymers, be it proteins, gelatins, so they are polymeric in nature. So we have a dispersion of macromolecules, and that is why they are kinetically stable. Sorry, thermodynamically stable. But if we consider the lyophobic colloid, since there is no affinity between the dispersed phase and the medium, there cannot be any solvation. Solvation is not possible. The dispersed phase is not solvated by the medium, and so their thermodynamic stability is less. In other words, the interfacial free energy is very, very high. So they want to go to lower free energy state, that is the aggregated state, agglomerated state, or what we call coagulated state. And that is why they often coagulates. I think it's clear. Okay, now let us move to the basic criteria of thermodynamic stability. So when we want to explain the stability of colloid, we have to go for the Gibbs free energy. So if you see here, del Z naught, just I'm taking just 1 minute. Okay, I'm back. So if you see here, the del Z naught expression, that is standard Gibbs free energy of formation for colloid, that is often expressed as gamma SL. Here gamma represents the interfacial surface tension into del ASL. So del A is the surface change in surface area, the solid liquid surface area. So this is the general expression for Gibbs free energy of formation for colloid. Now if you see, in case of hydrophilic colloids, this interfacial surface tension is negative, very less. So del Z naught is negative, and it is a highly stable state which is thermodynamically feasible. But in case of hydrophobic colloid, as we have already discussed, the interfacial surface tension will be very high, and that is generally positive, greater than 0, and so del Z naught is positive, and the process is not thermodynamically feasible, and it is a thermodynamically unstable state. I think it is clear. Okay. So this is one question that was asked by the Guwahati University in 2015. So why colloidal solutions are thermodynamically unstable? So the discussions that we have so far made regarding the thermodynamic stability, that is enough to answer this particular question. Okay, so when we here, if you see in this question that they have generalized colloid solutions, so we have seen that not all type of colloids are thermodynamically unstable. The lyophilic are stable, but here we have to speak about the lyophobic colloids. But if we can provide a discussion that lyophilic colloid do have thermodynamic stability because of negative interfacial surface tension. Del Z naught is negative. But basically, I think this will help you to answer this particular question. In between, if you have any queries, you can ask, okay, in between my lectures. Okay. Now, let us move to another the basic topic now. So as we have seen here, that colloids, they are unique in the sense that they carry electrical charge. And that is also related not only to their stability, but also to their structure and properties. But again, one thing should be noted. This charge is generally carried by lyophobic colloid. Lyophilic colloid may not carry charge. They may be neutral. In fact, most lyophilic colloids are neutral species. But we say that colloids are always electrically charged. They carry some positive or negative charge. Yes, the generalization is always for lyophobic colloid. So you have to remember that lyophobic colloids always carry positive and negative charge. Lyophilic colloid may be neutral. In fact, they are mostly neutral. And now let us move to what are the basic concepts behind the origin of charge. And the basic concept behind the origin of charge, one of the preliminary concept, is the dissociation of molecule forming colloidal aggregates. So molecules that do form colloids, they may dissociate, and this dissociation may give rise to positive and negative charge. Okay, so they may undergo dissociation or they may undergo ionization. So I have given two examples here. The first one, these are both are surfactant molecules. The first one, if you see, it has 16 carbon. If you see the carbon molecules here, there are 16 carbons, and it is called cetyl 16 carbon. And we have three methyl groups: cetyl, trimethyl, nitrogen is there with positive charge. Cetyl, trimethyl, ammonium, bromide. Bromide ion was there as a counter ion. So when they go to the dispersed stage, the bromide ion get removed. So there is dissociation of this molecule, and the bromide ion stays in the dispersion medium as counter ion, and the colloidal particles remain as positive charge. So they acquire charge because of dissociation on the head group, the hydrophilic groups. If you see the other surfactant molecule, in this tail there are 12 carbon. If you count, there are 12 carbon. So this is dodecyl. So we say sodium dodecyl. This is SO4 sulfate. Sodium dodecyl sulfate. Okay. So when we take it to the dispersed state, when it goes to the colloidal state and to the medium, this sodium ion is readily ionized, and this SO4 minus stays in the head in the hydrophilic part, imparting negative charge to the colloidal particles. So these are two classical suffix, and one is STAB, that is cetyl trimethyl ammonium bromide, and the second one is sodium dodecyl sulfate, we generally call SDS. Okay, and they have acquiring the cationic and anionic charges simply because of dissociation or ionization of their head groups. So this is one of the primary reason why colloids, mainly the lyophobic colloids, acquire charge. Now let us see the second point. So this is basically the other reason for the origin of charge on colloid, and that is presence of acidic and basic functional group. So most of the colloids, they do carry the carboxylic group, sulfonic acid group, hydroxyl or thioalcoholic group on their surface, or they may have some amide linkage. So in dispersion medium like water, okay, they readily dissociates these acids and hydroxyl group or the thioalcoholic group. They readily get dissociates to protonate the water, liberating the H+ ion, and goes to anionic state. On the other hand, the amide groups are protonated by the dispersion medium, and they readily goes to the positive state as NH3+ or NH2+ ion. So this basic presence of this acidic or basic group on the surface of colloids also impart themselves when they goes to the dispersed phase. So in the dispersion medium, polar dispersion medium like water can readily initiate their dissociation or their protonation to impart positive and negative charge to the colloid particle. So this is another basic reason for the origin of charge on colloid, presence of acidic and basic group. Another interesting example in this case are the proteins. As I have said, that proteins are one of the most biologically active colloidal particles. And we also know that they have both carboxylic acid and amide linkage. So presence of two functional group, one acidic and basic. So in acidic medium, the amide functional group and NH2 functional group is easily protonated and they acquire positive charge. In alkaline medium, the acidic carboxylic group readily loses a proton to provide a negative charge to the protein molecules. So we also know that at a particular pH, this is all controlled by the pH, that is acidic medium below very low pH, alkaline medium very high pH, and there is a particular pH which often we call isoelectric point, okay, and below which at which it remains in zwitterionic state. And at this stage, at the pH above the isoelectric point, which is the alkaline medium, it becomes negatively charged, and below the isoelectric point, which refers to the acidic medium, okay, that is they are positively charged. So at particular pH, they can exist as zwitterion, neutral molecule, but if the pH is much lower or higher than that isoelectric point, they can exist as positive or negatively charged colloidal particles. Okay, this is again, we have seen that this is due to the presence of the acidic and basic group in protein, so that they acquire the positive and negative charge. Then the most important theory that explains the origin of charge in colloid is the preferential adsorption of ion from the dispersion medium. So the colloidal particles of the dispersed phase, they absorb particular type of ion preferentially from the medium and acquire a particular charge. Now, what type of charges, ions are adsorbed? A colloidal particle easily absorb those ions from the dispersion medium which are in excess and are common to its own lattice. They should be in excess, and at the same time they should be common to their lattice. Then only they can absorb that ion. So even though they are both positive and negative ion, only one of the ion will be absorbed by the colloid. Classical example that we often we have seen in the higher secondary classes, in fact, is the formation of ferric hydroxide sol from the colloid, which we call the peptidation method. So ferric hydroxide sol, if we have ferric hydroxide precipitate, just add some ferric chloride solution to that precipitate. The ferric hydroxide goes to the colloidal dimension and becomes positively charged. So what actually happens here, that when ferric chloride is added, ferric hydroxide exists in a system in which it has a common Fe3+ ion. Ferric chloride has Fe3+ ion. Ferric hydroxide also has Fe3+ ion, so it has a common ion. And since the system has large amount of ferric ion that is in excess, so the ion which is in excess and common is absorbed. So ferric hydroxide will definitely absorb ferric ion and become positively charged. So that only that ion is absorbed which is in excess and which is common to its structure, to its chemical composition. So ferric hydroxide will not absorb any OH ion, but it will absorb ferric ion because ferric ion is present in the system. Some other examples. If we now consider the same ferric hydroxide sol, and it is now prepared by hydrolysis of ferric chloride with NaOH, that is alkaline hydrolysis. Now ferric hydroxide will be formed in NaOH. So ferric hydroxide and NaOH have OH ion common, and OH ion is in excess. So the ferric hydroxide will now absorb OH- ion and it will be negatively charged. So the first one we can say that it is ferric hydroxide. We can simply hydrolyze ferric chloride. If we simply hydrolyze ferric chloride, ferric hydroxide will be formed in ferric chloride. Okay, and now this is quite interesting because we can say that water should have OH ion, but and the problem is water is not a good electrolyte, and so there will be more of ferric ion than OH ion. All the OH ion that will be there, that will be used for formation of ferric hydroxide, and due to the presence of excess of ferric ion is absorbed. So when we hydrolyze ferric chloride in water, basically it should be hot water, we get positive ferric hydroxide colloid. But if we hydrolyze ferric chloride with some base like potassium hydroxide or sodium hydroxide, we get negative ferric hydroxide colloid. Similarly, to classical example, if we add silver nitrate to Ki, we get positively charged silver iodide colloid. But if we add Ki to silver nitrate, we get negatively charged silver iodide sol. So let us take the first case. So when we add silver nitrate to Ki, okay, silver iodide will be formed in Ki. So we have silver iodide and Ki. The common ion between Ki and silver iodide is iodide ion. So iodide ion is absorbed. But if you add Ki in silver nitrate, AgI will be formed in silver nitrate because now the solution is silver nitrate. So now AgI will be formed in silver nitrate. So in silver nitrate, AgI and silver nitrate has common Ag+ ion, and Ag+ ion is absorbed. So basically how they are formed, whether by adding Ki or to silver nitrate or silver nitrate to Ki, we are getting positive and negative sol. Okay, so silver iodide will preferentially absorb silver ion if it is formed in silver nitrate, but it will absorb iodide ion preferentially if it is formed in Ki. It will not absorb potassium ion because potassium ion is not common to its structure in Ki. Similarly, in silver nitrate, it will not absorb nitrate ion, okay, because nitrate ion is not common to its lattice. And finally, a rephrase of your high secondary classes. I took this table from the NCERT textbook. So depending upon this, whatever may be the origin. So when we say lyophobic colloids, remember again I'm using the word lyophobic colloids, which are generally charged colloid. We can readily distinguish that if there are any oxides, hydrated oxides, that is hydroxides, or oxides, okay, of metals, then they are always, generally they are positively charged. Then if they are basic dyes, like methylene blue, so what are basic dyes? They have OH functional group in their structure. So in the medium, they lose the OH group, okay. So basically, that is, they acquire positive charge, and so they are positive colloid. Similarly, hemoglobin is another example of positive Sol. So these classical systems of positive colloids, we should keep in mind that all metal hydroxides and all metal oxides, all basic dyes are positive colloid. Similarly, if we have any metal Sol, copper Sol, gold Sol, silver Sol, they are negatively charged. Any metal sulfide, arsenic sulfide, antimony sulfide, cadmium sulfide, they are generally negatively charged. Any acid dyes, famous Congo red dye, we know, they readily lose proton, so they acquire OH minus ion, okay, and they acquire negative charge. They lose proton, then they acquire negative charge. There some, depending upon the structure of the dye, the mechanism will be different, but since they lose H plus ion, they have to go to the negative state. And most of our common polymeric natural colloidal systems like starch, gum, gelatin, clay, charcoal, they are generally negatively charged. So we have to keep this table in mind, at least this generalization. We have already seen that charge in colloid depends upon what charge they will take depends upon various factors, and the primary factor is the situation in which they are formed. But still, we can have a generalization that all metal oxides and hydroxides, all basic dyes are positively charged, all metal Sol and metal sulfides, and all acid dyes are negatively charged Sol. So this table always you have to keep in mind, because this simple table can help you to answer short questions which are generally asked from colloidal section. Okay, so let us see few very short questions which has been asked by Guwahati University. So this was asked in 2014, a simple question. A positively charged silver iodide Sol can be prepared by adding dilute solution of NaI to slight excess of dilute solution of silver nitrate. So you are adding sodium iodide to silver nitrate. So why the colloidal particles are positively charged? So here it is definitely, the theory is preferential. We have to use the theory of preferential adsorption of ions. So when we add sodium iodide to silver nitrate, silver iodide Sol will be formed in silver nitrate. That we have to keep in mind, that silver iodide Sol will be formed in silver nitrate, will be formed in a system which have large amount of silver ion and nitrate ion. Since silver ion is common and it is an excess, it is preferentially absorbed by the silver iodide ion. soul, and so it becomes positively charged. So this is nothing but an explanation of the preferential adsorption of ion. Even this type of questions are also asked. Okay. Another that was asked in 2018. If when freshly prepared precipitate of ferric hydroxide is treated with water and ferric chloride solution, ferric hydroxide is converted to colloidal solution. That we know this is peptidation. So the question that is asked is, what is the role of ferric chloride in this process? Again, the same preferential adsorption of ions and electrostatic repulsion. So at first ferric hydroxide was precipitated. Okay. Now since it is treated with ferric chloride, now ferric hydroxide will be in a solution where there is large amount of ferric ion, and ferric hydroxide and ferric ion has a common ferric ion, so Fe3+ is common, so it is preferentially adsorbed, and when it acquires this positive charge, because of the presence of charge, these ferric hydroxide precipitate particles which were earlier precipitated, now the particles of this precipitate, they will now go apart because of electrostatic repulsion, because earlier they were neutral, now they are charged particles, so they will not associate, not agglomerate as precipitate, but they will now just simply split apart. When they split apart, they goes to the colloidal dimension. That means their size becomes within 1 to 1000 nanometer, and thus the precipitate get dispersed, resulting in the formation of a stable positive soul. So this is nothing but the concept of peptidation and the preferential adsorption of ion. Okay. Now let us move to the most important aspect of colloidal stability by electrostatic approach, and that is nothing but the electrical double layer. So this presence of an electrical double layer is the basic or the fundamental concept behind the electrostatic stabilization of colloids. So what is this basic concept? We know that colloid particle, they can acquire positive or negative charge by different ways, and one of the most common ways is by adsorption of preferential adsorption of ions. A negatively charged particle will attract positive counter ion surrounding the particle and vice versa. Once the colloids acquire the charge, so they will now attract some counter ion from the dispersion medium, and as a result what happened, an electrical double layer is generated. So it is the layer surrounding a particle of the dispersed phase, including the ions adsorbed on the surface, and a thin film of countercharged dispersion medium. So within the colloidal surface, near the colloidal surface, there will be a thin film of countercharged dispersion medium, and these two films, we call it Helmholtz double layer, or simply called electrical double layer. But one thing should be kept in mind, this EDL is electrically neutral. The total positive charge and negative charge on the surface and the medium will be same. So if we go to the structure of the EDL, you can find 3 different layers. First, it is the adsorbed ions, positive or negative, and that provide the charge to the surface of the colloid. So this is the surface charge. Then we have a layer of counter ion, which have charge opposite to the surface charge, and these are attracted by particle surface, and they are firmly attached by electrostatic attraction, which is called Stern layer. So Stern layer is the layer of counter ion. And finally, we have a diffuse layer. Between the Stern layer and the electrically neutral part of the dispersion medium, we have a diffuse layer which contains free ions and large amount of counter ions. This is called the Gohpur layer. So Stern layer is the firm layer, firmly attached layer, immobile layer, and the Gohpur layer is the diffuse layer. And the ions of the diffuse layer are affected by electrostatic force of the charged particle. They can move. So basically these are the three layers of an EDL. So if you can see here the picture of an EDL. So here I've given an example of a negatively charged colloid particle. So these are surface charges. As a result, they are absorbing, they are attracting positive counter ions that constitute the Stern layer. And after the Stern layer, we have this diffuse layer, which is called the Gohpur layer. So here the EDL will be diffuse layer and the Stern layer, okay, together with the will be the EDL. Now one interesting thing of this EDL is that the electric potential within the layer has a maximum value on the surface. That is the, if you see the surface potential here, okay, it is maximum, okay, at the Stern layer. So this is called the Stern potential. The potential drops with increase of distance from the surface and reaches zero at the boundary of the electrical double layer. It becomes zero here, and when it becomes zero, the double layer ends. The surface potential becomes zero. So when a colloidal particle moves in the medium, a layer of surrounding liquid remains attached to the particle. So when it moves, a layer of counter ion also moves. And this layer, the boundary of this layer is called slipping plane or the shear plane. So this is the slipping plane here. So when this colloid move, not only this counter ion but another layer shown by the red circle here, okay, the pink circle here, okay, this layer will also move. So the sphere that is shown, that the whole sphere will move. We have the Stern layer, the nearly blue-violet circle, and we have the diffuse, the slipping plane with the Stern layer, okay, and the value of electric potential at the slipping plane, that is called the zeta potential. And as you know, this is one of the most important parameter to quantify or quantitatively study the stability of colloids, or basically the electrostatic stability of colloid, the zeta potential. So since I will not talk about electrokinetic phenomenon, I will not discuss more on zeta potential, okay, but you have to remember that it is the potential at the shear plane, that is the slipping plane, okay, and that is called the zeta potential. So the surface potential is maximum on the Stern layer and zero where the EDL ends, and in between the potential on the shear plane or the slipping plane is called the zeta potential. So this structural feature of EDL should be very much clear. Now if you see in the EDL, okay, certain things are not explained regarding, basically it has this particular aspect, though it was worked initially by Helmholtz, who gave us the concept of the double layer, and then modified by Stern, who gave us the concept of the Stern layer, and finally Gohpur, okay, and the concept of zeta potential came up. Still, many aspects of colloid, basically the concept of potential energy, was not discussed in the EDL. So this was now more quantitatively studied by 4 scientists, Darrang, Landau, Farvey, and Overbeek, and they developed a theory in 1940s to explain the stability of colloid, and that is called the DLVO theory. What does this theory basically says? This theory suggests that the colloidal stability is determined by sum of van der Waals attractive interactions and electrical double layer repulsive forces that exist when between particles when they approach each other through boundary motion. So these two forces, van der Waals attraction and electrostatic repulsion, okay, their combinations determines how stable is a colloid. The van der Waals attractive forces depends basically on the size of the particle and also on the chemical nature, what type of bond it has, what type of functionality it has. And the electrostatic repulsive forces depends on the surface charge. More charge, more repulsion, the density of the charge, and also the thickness of the double layer. If the double layer is thick, okay, the electrostatic repulsive forces will be higher. So the density, surface charge, and thickness of the double layer will determine the electrostatic repulsive force. So there are some mathematical expressions here. According to DLVO, the repulsive potential energy, okay, that is the electrostatic repulsion on each particle of radius A is given by this expression. I have skipped the derivation part, so we only need qualitative aspect. So this is derived as A small a square zeta square. Zeta is the symbol for zeta potential divided by r e to the power minus sr. When the radius is smaller than the rd, here is the thickness of the double layer, and the radius of the particle is smaller than the thickness. And if the radius of the particle is greater than the thickness, then this exponential is changed into a series of logarithmic series ln 1 plus e to the power minus sr. Okay, now what are the parameters here? So A is definitely a constant. R is the radius, sorry, it is the separation of the centers of the spheres. S is the separation of the surface of the particle. So S and R are related. S is equal to R minus 2A. A is the radius of the sphere. So R is the separation between the centers of the sphere, and S is the separation of the surface. Physical separation is small s from the surface, and from the center it is smaller. So R minus 2A, 2 radius gives you the diameter, so is S. And RD is the thickness of the double layer. So this empirical relation was derived for the repulsive interaction. And for attractive interaction, that is the van der Waals interaction, it derived another DLVO. These four scientists came to another empirical relation. VA is equal to minus B by S. So B is another constant. Now, using this potential energy expression and considering the electrical double layer as a simple electrical condenser, we can treat the electrical double layer as an electrical capacitor or as an electrical condenser. So treating it as an electrical condenser, okay, through DLVO theory, an expression was derived for zeta potential, which is very interesting. Zeta potential, zeta is equal to 4 pi eta mu by z. Okay, so I have this term by epsilon, sorry, 4 pi eta mu by epsilon. So eta and epsilon, they are definitely the coefficient of viscosity, and epsilon is the dielectric constant, and mu is the mobility of the particle. So this is zeta potential depends upon viscosity, the mobility, the dielectric constant of the system. Now in this expression, one thing is clear, that dielectric constant and zeta potential are inversely related. So if you go to the question papers of Guwahati University, you will find in 2 or 3 previous years, I think in 2017 and 2019, one question was there: how zeta potential is related to dielectric constant. So this is the relation between zeta potential and dielectric constant. So it is through DLVO theory, the relation we can express it. So this is in fact the significance of the DLVO, that when the dielectric constant decreases or increases, the zeta potential correspondingly increases or decreases inversely. So if the dielectric constant increases, the zeta potential decreases. So let us consider, and vice versa. So suppose the dielectric constant of the system increases. Okay, so this can be increased by increasing the polarity, by other factors like temperatures. So if it happens, what will happen? The zeta potential will be lowered, and ions of opposite charge to that of the colloidal particle will get adsorbed. Once the zeta potential will be lowered, okay, opposite ions, the counter ions will be not counter ion, ions of opposite charge will be adsorbed on the colloidal particle. Okay, these are counter ions. So what will happen? This will reduce the mutual repulsion between similarly charged colloidal particle. Why? That means they will be neutralized. They already have some charge, and because of lower zeta potential, now the counter ion will be adsorbed, neutralizing their charge. If there is some zeta potential, the counter ion will simply form a EDL, but that EDL will be lost now. Okay, the counter ion will simply come and neutralize the colloidal particle. There will be no electrostatic repulsion. The colloidal particle will come closer. They will aggregate, and that will be bigger than the colloidal dimension, and that means they will undergo coagulation or flocculation. And that is the important significance of DLVO, that for the stability of the colloid, the most important thing is the dielectric constant of the system should be very low, should not be allowed to increase, or the zeta potential should not be allowed to decrease. So if the zeta potential decreases to a critical level, then there will be neutralization of the colloidal charges, and this will induce immediate coagulation or flocculation. That is, when zeta is small, the resultant potential energy is negative. Van der Waals attraction will predominate over electrostatic repulsion. So after VR and VA, okay, VA will be higher than VR, and there will be coagulation of the soul. Now the DLVO theory gave us some energy barriers. So mainly there are 3 energy barriers. We say primary minimum. So if we plot potential energy against interparticular distance, we get in the curve of the potential energy curve, we get 3 peaks, 2 lower peaks which are called minima, and 1 upper peak which is called maxima. The first lower peak, it is called primary minima. The second lower peak is called secondary minima, and between these 2 peaks, the hill, okay, that is the energy barrier, that is called the primary maxima. So let us start with the secondary minima. The secondary minima is nothing but the flocculated state. Okay, so this is a flocculated state. So now, and the primary minima is also nothing but the state of lowest energy. So where the particle stay, that is the coagulated state. Once they go to the coagulated state, okay, their potential energy will be minimum. Now if they want to go to the colloidal state, they have to overcome the energy barrier, and that is called the primary maxima. Okay, so when particles comes closer, they must collide with sufficient energy to overcome the energy barrier provided by the primary maximum. And the secondary minima is also another flocculatory state. Even if they undergo the energy barrier, they may go to a second flocculation state, another minima state. Okay, and definitely, but still they have to cross the energy barrier to go to the minimum state. Still they will be in the not in the minimum energy state. Still they will be unstable, and then again they have to cross this barrier to reach the primary minima. So primary minima is where the actually the coagulated state exists. That means at this minima, the potential energy is minima, the zeta potential is minimum, and at this stage the zeta potential is maximum. So this is the basic energy expression of DLVO theory. Now let us move to the stability of lyophilic and lyophobic colloid. So now through DLVO, what we have learned is that in case of lyophobic colloid, the presence of same electrical charge, repulsive interactions prevent coagulation. They have same electric charge, repulsive interaction is prevalent. Okay, and magnitude depends upon the magnitude of surface charge and the thickness of the double layer. And these two factors are again these factors determine what is the value of the zeta potential. So through DLVO, what we can conclude is that stability of the colloidal system is governed by the zeta potential. Higher value of zeta potential indicate that the resultant potential energy is positive. So electrostatic repulsion predominates over van der Waals attraction, and as a result, the colloid remain in the stabilized state, that is dispersed state. They will not agglomerate, they will not coagulate. And we have already seen that for zeta potential should be higher, the dielectric system should be lower. Okay. Then if the value of zeta potential is low, this indicate that the resultant potential energy is negative. So in that case, what will happen? The van der Waals attraction will predominate over electrostatic repulsion, and there will be readily coagulation. So this is, if you see this discussion, this is totally true for lyophobic colloid. Okay, only in case of lyophobic colloid, because we can say that all lyophobic colloid are electrically, they carry electrical charges. But we cannot generalize this for lyophilic colloid. Why? Because as I have told you that lyophilic colloid are mostly neutral. They may have positive charge. Another interesting thing is, in lyophilic colloid, the dispersed phase and dispersion medium has strong affinity. So solvent plays the most important role in its stability. Whether they are charged or they are not charged, they will be solvated. Suppose they are charged, okay? So this lyophilic, they will be surrounded by water dipoles. Suppose they are positively charged, the negative end of the water dipole, that is oxygen end, will be attracted toward its surface. So they will be cased by water molecule, solvated by water molecule. Even if they are negatively charged, they will be solvated. They will attract the positive end, that is the H plus end of the water dipole, and the water molecule will now stick to the surface and trap it, case it, and these solvent cases will now act as a barrier preventing their coalescing. So they will, even if they are charged, there will be no electrostatic influences. Okay, but at the same time, they will not allow the particles to come closer. So these spheres, the cases, will prevent them from coming in contact, coming to a particular distance, so that they can associate to nano size. So that is prevented by the solvent. So what we can say that solvation is the primary cause of stability of lyophilic colloid, or we can also say that they are hydrophilic. Okay, hydrophilic colloid or lyophilic colloid, whatever you say, they are because of solvation. So when we say hydrophilic, it is water, and when we say lyophilic, generalize any solvent. Okay. So stability of lyophobic is because of the zeta potential, that is the presence of electrical sources, and stability of lyophilic colloid is due to the solvation of the lyophilic or hydrophilic colloids. Now, we have seen that thermodynamically the lyophobic colloid are unstable, okay, and they can readily coagulate. So they are what we call flocculate. So they has to be protected. So how lyophobic colloids are protected from coagulation? So this is done by adding lyophilic colloid. So to protect the lyophobic colloid, we generally use lyophilic colloid. Addition of lyophilic colloid rendered them less sensitive toward precipitation, even on adding electrolyte. So this phenomenon of preventing the coagulation of lyophobic salt due to addition of lyophilic colloid, it is called the protective action of the lyophilic colloid. The lyophilic colloid, how they protect? So it has been said that the lyophilic colloid simply get absorbed on the lyophobic colloid, entrapping them, encasing them like solvation. Okay, so they are cased, and this prevent the approach of the lyophobic colloid closer. Okay, so they cannot coagulate. So that is the most probable explanations, that lyophobic colloid simply get absorbed and entrap them in the form of loops, in the form of a case, and as a result the particles cannot approach each other, okay, and they cannot coagulate. Okay, so in this case, one question was asked in the Gohpur University examination 2015. Addition of NaCl solution to gold salt result in coagulation of the salt, but in presence of starch, addition of NaCl solution cannot affect the precipitation or coagulation of gold salt. Explain this observation. So first of all, we have to see what is the nature of the gold salt. As we have seen in the table that I have brought from the NCERT textbook, that gold salt are nothing but negative salt. All metal salts are negative, and they will be coagulated by and another form, they are hydrophobic, and so they, when we add sodium chloride, sodium ion will be absorbed on the surface, and as a result what will happen, due to electrostatic attraction, and as a charge is either reduced or neutralized. Sodium ion are absorbed on the surface, it is already negative, but because of addition of sodium chloride, sodium ion will get absorbed. Already there is some absorption of negative ion, and addition of NaCl will provide another ion which is opposite in charge, and it will either totally neutralize the charge or reduce it to a very low level. EDL will collapse, that is zeta potential will be lowered to critical value, and it has been found that critical value is 0.02 fall. If the zeta potential is less than that, okay, there will be no electrostatic repulsion. So this happens that when sodium ions are get absorbed, the negative charge over gold salt is neutralized, electrostatic repulsion diminishes, and the salt particles, because the zeta potential decreases to a lower level, lower than the critical value, and they can come closer and flocculate or coagulate. This is the role of electrolyte in coagulation. Now, second part, when we add stars, stars is a lyophilic soul. So that is the protection role. So gold soul, in presence of stars, what will happen? The stars particles, stars molecule will case the gold soul. They will be absorbed over the gold soul. They will case it, and they will prevent addition, absorption of sodium ion. Sodium ion will no longer be absorbed. So as a result, they cannot come closer. Neither absorption of sodium ion can make it neutral, nor one way, and another way, since the lyophilic souls are absorbed, they form a case, and because of that also the particle cannot come closer. So neither they can come closer because of electrostatic forces, nor they can come closer because of van der Waals forces. Okay, so they cannot coagulate. So that is, the stars plays the role of a protective colloid for the gold soul. Okay, another question that was asked in 2016: why protein in water solution undergoes coagulation in presence of alcohol? So in presence of alcohol, so one thing you have to keep in mind, that alcohol can denature protein. So if you see the structure of protein, it has primary, secondary, and tertiary structure. And during the denaturing, only the primary structure remain intact. The secondary and tertiary structure collapses. So what alcohol do? Alcohol denature and unfold the protein structure, and because of this, the protein molecules can come closer. So in presence of alcohol, protein in water solution undergoes coagulation due to denaturing and unfolding of the protein structure. Alcohol denatures a protein. How? By disrupting the intramolecular hydrogen bonding between the side chain. So within the protein molecules, within the side chain of the protein molecule, there are some strong intramolecular hydrogen bonding, and these are disrupted by alcohol, which has a strong negative hydroxylic group. And when this is disrupted, the tertiary structure collapse. Another thing is, the alcohol molecule also compete with the amino acid residue in forming new hydrogen bond, which distances the side chain from each other. These also initiate breaking of its tertiary structure. Besides, it also interacts with the hydrophobic residue in protein. The protein has a hydrophobic residue, okay, and that residue presently in its core is destroyed, and as a result, its structure, both secondary and primary structure, get collapses, and it is denatured. Because of denaturing, it unfolds and readily coagulates. Another important thing you have to keep in mind, that when we add alcohol to protein in water system, the dielectric constant also decreases, and there is also dehydration of the protein. The water molecules are pulled from the protein, so this also decreases the solubility of the protein in solution. So because of all these facts, proteins are precipitated, they coagulate from their solution when alcohol is added. I think this is sufficient for you. So why protein in water undergoes coagulation in presence of alcohol? So alcohol plays, basically it destroys the tertiary structure by disrupting the intramolecular hydrogen bond between the side chain. It also compete with the amino acid for hydrogen bonding, new hydrogen bonding. That also split apart the sides, pushes the side chain, destroying the tertiary structure. It also interacts with the hydrophobic residue, destroying the hydrophobic core. It decreases the dielectric constant. It dehydrates the proteins. So all this results in denaturing, unfolding of protein, and the solubility of protein decreases and it coagulates to form precipitate. Okay, let us come to the quantitative aspect of coagulation, and that is called gold number. So this was introduced by Sigbondi, and gold number. So it can be defined as the minimum amount of hydrophilic colloid in milligram required to prevent coagulation of 10 ml of a gold sol on addition of 1 ml of 10% NaCl solution, which prevent color change from red to blue. So gold sol is basically red. It is a negative colloid. When we add NaCl, it will coagulate, and when it coagulates, it will color change to blue. So the quantitative aspect, the minimum amount of a hydrophobic colloid that can prevent this change in color, that can prevent the coagulation of gold sol, when we add 1 ml of 10% NaCl to 10 ml of gold sol. So if you take 10 ml of gold sol, add 1 ml of 10% NaCl, it will immediately become blue. But beforehand, if you add some lyophobic colloid, this color change can be prevented, coagulation can be prevented. So what amount of the lyophobic colloid you need? Hydrophilic colloid you need in milligram. The minimum amount is called gold number. So smaller the gold number, the less amount you need. We say higher is the protective power of the lyophilic colloid. So these are some gold number. If you see the lyophilic substance like gelatin have a very low gold number, so their protective action is very high. And stars or potato stars or normal stars, they have very high gold number. Their protective action is very less. So like gold number, we have another number that was introduced by Oswald. Gold number was introduced by Sigbondi, which is another pioneer in colloid chemistry. And similarly, Oswald introduced another number called Congo-Rubin number. So it is defined as amount of protective colloid, that is the lyophilic colloid in milligram, the same, which prevent color change from red to violet in 100 ml of 0.01% Congo-Rubin dye, to which 0.16 gram equivalent of KCl is added. That means to a Congo-Rubin dye, if you add KCl, it will undergo coagulation. To prevent the coagulation, what amount of lyophilic colloid is required? The minimum amount in milligram. That is called the Congo-Rubin number of the protective colloid. Okay. Now let us see a few problems. This was asked in 2018, I think, Gohpur University. Very simple problem based on gold number. The gold number of gelatin is 0.01. Calculate the amount of gelatin to be added to 1000 ml of a colloidal salt of gold to prevent its coagulation before adding 1 ml of 10% NaCl solution. So we have gelatin. Its gold number is given to us. We have to calculate what amount we need to prevent coagulation of 1000 ml of gold sol by adding 1 ml of 10% NaCl solution. Okay, so let's start from the gold number. Gold number of gelatin is 0.01. What does it mean? This means that 0.01 milligram is the minimum amount of gelatin required to prevent 10 ml of gold sol on addition of 1 ml of 10% NaCl. That is the basic definition of gold number. So if you add 0.01 milligram, 10 ml of gold sol can be prevented from coagulation. So amount of gelatin required to prevent 1000 ml. For 10 ml we need 0.01 milligram. So for 1000 ml, how much we'll need? We'll need 1 milligram. 0.01 by 10 into 1000. So we need only 1 milligram to coagulate, to prevent the coagulation of 1000 ml of the colloidal gold sol. So since okay, so this is the answer that we need. Very simple question, only 1 or 2 marks are 2 marks was asked, that is in 2018. Let us see, this was asked in 2016, I think. I forgot to give the year here. 10 to the power minus 4 gram of gelatin is required to be added to 100 ml of a standard gold sol to prevent its coagulation by adding 1 centimeter cube of 10% NaCl solution. Calculate the whole number of gelatin. So here we have to calculate the whole number of gelatin. And it is said that we have 10 to the power minus 4 gram is required by 100 ml of gold sol. Gold number by definition is how many milligram we need to prevent coagulation of 10 ml. So we have to find out that for 1000 ml, centimeter cube is ml, we need 10 to the power minus 4. So for 10 ml, we need 10 to the power minus 4 into 10 by 100. That is, we need 10 to the power minus 5 gram. So amount of gelatin we need for 1000 ml is 10 to the power minus 4. So for 10 ml, it is 10 to the power minus 4 gram, 5 gram. Let us convert it to milligram. It is 0.01 milligram. So that is the goal number. Okay. Let us see another question. Coagulation of 100 ml of colloidal gold solution of gold is completely prevented by addition of 0.03 gram of hemoglobin before adding 1 ml of 10% NaCl. Find out the goal number of hemoglobin. So this was also asked in Guwahati University. So all these questions are taken from Guwahati University board examination papers. So again, you see another very simple question. For coagulation of 100 ml, okay, we need to prevent the coagulation, we need 0.03 gram. So to amount of hemoglobin needed to prevent coagulation of 10 ml is 3 mg. So the goal number is 3 mg. Quite simple. So for 100 ml it is given, we need 0.03. So for 10 ml, we need 3, and definitely the goal number will be 3 milligram. For 100 ml, we need 30 milligram, that is 0.03 gram. So for 10 ml, we need 3 milligram, and that is the goal number. Okay. Now, Rajuda. Hello, Rajuda.
Hello.
Time kiman loke ase?
Time aru 2-3 minute ase. Na 8:30 loke loi thwa asile.
8:30
extra time jabo.
10 minutes man pam ne aru?
Aru 10 minutes mane 1.5 ঘন্টা লই থোৱা
ঠিক আছে
5 মিনিট কমপ্লিট কৰিব নোৱাৰিম আৰু আমি ডিসকাশন কৰি দিম
ঠিক আছে হ'ব দিয়া
ষ্টুডেন্টে কিবা সুধিব পাৰে
okay so okay
Palash
hello
Palash good
কোৱা
ভাল হৈছে কোৱা কৈ থাকা কেতিয়া শেষ কৰিবা
5 মিনিট
okay Rajuda
okay
Rajuda am I audible
okay ঠিক আছে 5 minutes more
5 minutes
okay
so this is Hardiscal's rules. I will not go in details. We already know that coagulation is prevented by opposite ions. Greater the charge of the ion, more will be the coagulation. So only one thing I want to clear here, that is often puzzled by, the students are often puzzled by one fact. Coagulation or flocculating power and coagulation and flocculating values are different. Okay, so I am skipping the Hofmeister series. So there is one aspect, that is flocculating value or coagulating value, and there is in Hardiscal's rule what we know, it is the coagulating power or flocculating power. So these two terms should be very much clear in mind. So what is flocculating value? It is the number of millimoles of an electrolyte required to bring about coagulation. So how many millimoles, remember millimoles of an electrolyte that is required to bring about coagulation of 1 liter of colloidal solution. So, and flocculating power is inversely proportional to the coagulating power. Flocculating value is inversely proportional to the coagulating power. So if the coagulating power is high, that is the flocculating value will be low. That is the difference. So sometime in question paper it is asked coagulating value. Coagulating value is flocculating value. Coagulating power or flocculating power, they are different. They are inverse. So sometimes flocculating value is also called coagulating value. I'll show you some question asked in the GU paper. So flocculating value is inversely proportional to coagulating power or flocculating power. And in fact, it is inversely proportional to 1 by Z to the power 6, where Z is the valency of the ion. So suppose we have different ions and monovalent, divalent, trivalent, and tetravalent. If you see 1 by 4 to the power 6, 0.025, that means only 0.025 millimoles can prevent coagulation of a colloid, 1 liter of a colloid. If it is tetravalent, but 100 milligram is required to prevent it coagulation of 1 liter of colloid if it is monovalent. So two things you have to remember, flocculating value is the millimoles of an electrolyte required to prevent coagulation of 1 liter of colloid. It is inversely proportional to coagulating power or flocculating power, and it is inversely proportional to Z6, Z to the power 6, that is, that is the valency. Okay, let us very fast swiftly discuss few questions asked in GU. So that was asked in 2014. Arsenic sulfide salt, the flocculating value of NaCl and KCl are almost same, though calcium chloride solution has less flocculating value. For arsenic sulfide salt, if you add NaCl and KCl, the flocculating value will be same. But if you add CaCl2, the flocculating value will be much less. So you see arsenic sulfide are negatively charged, so they will be coagulated by positive ion, and sodium ion and potassium ion cannot coagulate it much than calcium ion, because calcium ion has more valency. So according to Hardiscal's rule, calcium ion will coagulate arsenic sulfide more than sodium ion and potassium ion, and since they have similar valency, they have almost similar coagulating power. But coagulating power is inversely proportional to flocculating value. So since coagulating power of calcium ion is very high, its flocculating value will be very less. That is the concept. So there is another that was asked in 2018. So for coagulation of 100 ml of arsenous sulfide salt, 5 ml of 1m NaCl is required. So what is the flocculating value of NaCl? So for 1000 ml of 1m NaCl, we need 1 mole, that is our mole concept. So for 5 ml of 1m NaCl, we need 0.005 moles, that is we need 5 millimoles. That is what we have to find out. For 5 ml of 1m NaCl, how many millimoles of NaCl you need? 5 millimoles. Okay, so the amount of NaCl required by 100 ml of arsenous sulfide salt for complete coagulation is 5 millimoles, because you need 5 ml of 1m NaCl and it contains 5 millimoles. Okay, so but what is flocculating value? It is the amount of the ion required to prevent coagulation of 1 liter. It is about, for 100 ml we need 5 millimoles. For 1 liter, 1000 ml, how much we need? 50 millimoles. So coagulating power, sorry, flocculating value or coagulating value of NaCl is 50. Now this was another asked in 2015. For 0.1 barium chloride solution, to coagulate 1 decimeter cube arsenic sulfide salt, how much barium chloride you need in volume? Barium chloride flocculating value is given 4. So since flocculating value is 4, so to prevent coagulation of 1000 ml, that is 1 decimeter cube is 1000 ml. So to prevent coagulation of 1000 ml of arsenic sulfide, we need 4 millimoles. of barium chloride because its flocculating value is 4. Now we can simply use the concept of mole. Molarity is number of moles by volume. So volume is number of moles by molarity. So 4 millimole is 4 into 10 to the power minus 3 moles. Molarity is 0.1. So we need 0.04 liter, or we need 40 ml to prevent the coagulation of 1 ml of 1000 ml of arsenic sulfide sold. And that was another asked in one of the GU exam. Flocculating value of arsenic sulfide by HCl is 30 millimole per liter. So here what we have to do is calculate the mass of H2SO4 required for 250 ml. So the question is interesting. Flocculating value of HCl is given and they are asking you what amount of H2SO4 is required. So how will you find out? We'll simply by comparison of HCl and H2SO4. H2SO4 is dibasic. So if flocculating value of HCl is 30, flocculating value of H2SO4 will be half, 50 millimole. So H2SO4 required for 1000 millimole, 1000 ml is 50 millimole. So for 250, we need 15 by 4 millimole. Now we have to convert this millimole to gram. That we can easily do it from molecular mass of H2SO4. Molecular mass is 98. So 1 mole or 10 to the power minus 3 millimole is 98 gram. So 15 by 4 millimole is 0.3675 gram. So this much gram of H2SO4 is required. So there was another asked in 2016. It is asked that in case of coagulation, flocculating value of potassium ferrocyanide is less than that of potassium sulfate. But if you see, it is interesting that here ferric hydroxide is a positive colloid. It is coagulated by negative ion. In potassium ferricyanide, it is 3 minus ion, not 4 minus here. It is 3 minus ion. I made a mistake. And for potassium sulfate, it is 2 minus ion. So coagulating power of FeCN6 3 minus ion is higher. So its flocculating value is less because flocculating value is inversely proportional to coagulating power. So with this, I end my talk on colloid. And now if you have any queries, we can answer it. Rajuda?
Thank you, Dr. Palash Saikia, for your nice presentation. Especially for your collecting the questions actually. So I think students will get benefited from today's lectures. But here I'd like to interact with you. One of our research person is still present here, Dr. Pankaj Hazarika.
Yes, Rajura.
Dr. Hazarika, please
Yes.
give your valuable comment.
Okay, sure. So it's a very good evening to all the participants of today's lecture. So this lecture will help you all to go through your syllabus and will also be beneficial for your coming exam. I must thank Dr. Palash Saikia, a renowned academician and quizmaster of this region, for such an informative and syllabus-oriented lecture. So in this occasion, I would also like to thank the organizers of this lecture series, Principal Sir of Chaiduar College and the HOD Chemistry, Dr. Raju Jha, for organizing such a syllabus-oriented lecture series in such a pandemic situation. Hope this will be beneficial for our students. And again, all the best to the students for your coming exams. And thank you, Palash Muni, for such a informative lecture. Okay, Rajuda. Rajuda, it is over to you now.
Thank you, Pankaj. So we have like to interact with our students. So I have seen one student, Sagar Sen.
Thank you, sir.
Please share your experience.
At first, my professors and my special thanks to today's lecturer, Dr. Polamani, sir. The slide that's been shared today have everything, and by everything I mean all the things we need for our 6th semester exams. So thank you, sir, and wish luck to all my batchmates for the upcoming exams. Thank you.
Okay. Thank you, Sagar. We have another student, Hitesh, I think. Is his line? Hitesh, please
Yes, sir.
share your experience.
Sir, thank you for the such a informative lecture on colloids. So it is really helpful for our upcoming examination. So thank you, sir. Thank you so much.
So we have another student, Rituborn Sharma. Rituborn, please share your experience.
ধন্যবাদ ছাৰ, বহুত ভাল লাগিলে ইমানখিনি হেল্প কৰাৰ কাৰণে আমাক।
Thank you. Thank you.
So thank you, everyone. So especially thanks Dr. Palash Saikia. Now one of our colleagues, Udesna Priya Kakuti, who is still present with us, I offer to give her a vote of thanks.
Yes, sir. Thank you, sir, for this session and giving your precious time to us. And I appreciate the presentation. It was very much informative, and this will be benefited for our students. And you have also discussed the previous year questions while discussing the topic, and this will be helpful for the students. Thank you, sir.
Thank you.
Okay. Thank you, everyone.
Thank you, Adita.
Thank you, sir.
Thank you.
Finally, I should thanks everyone.
Thank you, sir.
Bye. Good night.
Good night.
Thank you,
Good
sir.
night, sir.
Good night, sir.